Hi everyone, thanks a lot for coming to our tutorial. And the title of our tutorial is Formal Analysis, Verification, and Design of Safety Critical CPS. And this tutorial will be given by Lei Bu, which is me, and Qixing Wang, Naijun Zhang, and Mingshuai Chen. I'm from Nanjing University, and Qixing is from Hong Kong PolyU. Naijun is from Chinese Academy of Science, and Mingshuai is from Acheng University. And here is the content of our tutorial. First, in the first session, I will show how we do the verification of hybrid system, and then we extend to the verification of CPS system. And in session 2, Qixing will talking about using design patterns to test CPS software. And in the last session, Naijun and Mingshuai will talk about how to handle the timing delays in CPS systems. And now it's first session, my part, which is from boundary reachability analysis of linear hybrid to verification of industrial CPS. And this is joint work with Ding Bao, Yang Yang, Jianhua Zhao, Xuandong Li, all from software engineering group in Nanjing University. Okay, here's the outline of my talk today. First, I will show the preliminary knowledge about what is hybrid systems and what are we talking about verification of hybrid automata. Then we will show our unique way of the bounded model checking of linear hybrid automata. Then we'll show how we extend that work to the online model checking of cyber-physical systems. And we will show some other extensions that we are working so far. And then I will go to the conclusion of the first part. Okay, first, what's hybrid automata? And we say hybrid system is systems that contain both continuous and discrete components. It has lots of practical examples. For example, embedded system controller via size circuits, and recently there are also many works using a hybrid system to explain in system biology, and it has been widely used in lots of safety critical areas. So because it's safety critical area, so you need to guarantee it's correct. And formal verification is one of the major techniques to do so. And basically, there are two ways of formal verification. One is serial proving, and the one is model checking. And now, today, we are talking about model checking. So for model checking, you need to have a formal model of the system. Then you do the state space computation, right? So here, the formal model we use is hybrid automata. And what is hybrid automata? It's a widely studied formal models of hybrid systems. It's a tuple, which we will not go to detail of it. Basically, the tuple consists of a finite state transition system and the differential equations in each location. And the differential equation makes the behavior of the system complex. For example, here's a picture of the water heater that I grabbed online. And if we build a model for it, basically it's a simple one, like this one. We have two nodes. One is off, one is on. One means the system is turned off. One means it's turned on. And you may notice here, in each location, we have a differential equation. We have x dot, right? So the x dot equals to -2. It means dx dt equals to -2. So x here is continuous variable, and the initial value of x is 20. But when the heater is turned off, the temperature of the water that it may goes down according to this differential equation, like dx dt equals to -2. Okay, so here for the x dot equals to -2, we call it a flow condition. Okay, you may also notice here, in the off the location, we have a expression says x should be larger or equal to 18 because invariant. It means if you want to stay in this location, in the off, then the value of x should satisfy this constraint. It's called invariant. And when the value of x is smaller than 19, then this jump condition, you may also call it a guard of the transition, it will be enabled. Then in this case, you can jump from the location off to on. And when you jump to on, then the differential equation will be changed to dxt equals to 4, and the invariant is x should be smaller than or equal to 22. And that's it. That's the system. So you may see the system very simple, but actually, because we have dxt here, this makes the system infinite state space, right? Because how many time spots there could be, right? During, like we say, from the time 0 to time 1, it's numerous. Okay, and for such system, like we can see all the constraints and the differential are linear. So we call it linear hybrid automata. It is a very special subclass of hybrid automata. And then for general automata, it could be like dxdt equal to sine x plus sine y and multiple something, right? It could be very complex. And here we are talking about one special subclass. Okay, so for the verification here, we're talking about reachability verification. Actually, reachability is one of the most important important questions in the safety verification. For example, if each small dot means the state of the system, and the arrows means transitions between states, then you're coming from here, the initial state, and suppose there is something bad, like the stop sign, and the reachability problem are asking like whether you can come from goes from the initial state to the stop sign. If it is yes, then it means the bad thing is reachable. It means the bad thing may happen. So reachability is very close related to the safety verification problem. And here, the target of our work is to find a sequence of states which may reach the target. Actually, as we say, the reachability verification of hybrid system is not that simple. The main question is, like, despite the discrete states, the discrete locations, the most difficult part is continuous part. For example, like if we stay in the location vi, and you have two valuation of the variables, say we have delta I and the gamma I, right? One means like in the time 0, and this means in time ti, something like that. And in this case, how can we say that these two states make a feasible behavior of the system? First, they should have a flow function, W, the big W. The function is from 0 ti to real. And we also need a first derivative, small w or big W. It's also from 0 ti to real. And we have like big W 0 equals to delta I x cubed for a variable x cubed. And we have like a WTI equals to gamma. It means, okay, in the first time spot, it's the value is delta, and after ti time, the value is gamma. And that's not everything. The most difficult part is here. For all values epsilon in the range from 0 to ti, we must have like the big W epsilon certified invariance in alpha vi. Like when you stay, like here, you stay in the location of vi, right? You keep staying there. So all the time spot, the valuation of the variables must certify the invariance. And we also have like during that time, the first derivative of W should be in the range of the flow condition, should in this range, something like that. That makes the thing difficult because it's infinite state space. Okay, so now we see the approach. Like for general approach, most studies using like overall approximation, like polyhedral or zone, something like that, to do the overall approximation of the state space of each location. Then they will compute like a geometric computation to see what will be the state space of the next step, and so on until they find a fixed point, something like that. And we can see lots of tools, famous tools using such method like high-tech, favor, and so on. But actually, the performance is not very good because, first of all, the verification, the reachability verification of linear hybrid automata is undecidable. It has been proven because the fixed point computation may fail. Now you cannot find a fixed point or something. And because you're using overall approximation, the result may be not that precise. And because you're using geometric computation is very expensive to use. So the dimension of the system that can be solved by such method is limited. By dimension here, we mean the number of continuous variables. And for example, in this system, the dimension here is 1 because we only have one continuous variable, which is x. Okay, let's move on. So as general model checking, like the computer state space computation is difficult. So researchers starting to think about the bounded model checking. What is bounded model checking? Bounded model checking means you want to search for potential behavior of the system, not in the complete state space, but within k-step. For example, suppose the big circle means the complete state space of system, and the red cross means bug. So for general model checking, what they do, they want to compute how large is the state space. Then after the computation, after they find the fixed point, after everything is finished, they will see, okay, whether the bug is inside or not, to check it. In this case, they can tell, okay, I have already traversed all the state space, and you see the bug here, right? So your system is error-proof. But for difficult systems, for complex systems, maybe it's difficult to compute the complete state space. In this case, then we can say, okay, I will not go to like all the state space, like forever, but we just to check the behavioral system like in k steps. You give us threshold, then we just check the behavior in this threshold. In that case, we don't need to compute that large state space, but maybe we can still find some bugs. That's the main idea, the intuition of bounded model checking. We call BMC, right? And however, for BMC of hyperlocal meta, the classical way is like they encode all the potential bounded behavior firstly as a huge SMT formula. Then when like they will consider all the possible directions, like when I stay in location 1, I will go this way, this way, this way. Then all these possibilities, they will put them together into one formula. Then they put to SMT formula, then ask SMT solvers, say these 3 to solve it. And in this case, if the graph structure of the system is complex, then you may face lots of different branches, and it will result in a huge SMT problems. And now we can see like in practice, like even we solving system with medium bound, we may face large SMT problems. Then SMT solvers are difficult to solve. Okay, it will be like this way. Like in our imagination, we can do a large enough bound to find some bugs, but in practice, you may result in this. You can just search space very shallow, and there is no bugs in it. Okay, so the main problem here is how to control the complexity. Like if we will still want to do a big step, then how to do it? How can we use SMT or other methods to check such state space? And now go to our method, which is bounded model checking of linear hyperlocal meta. And it's a systematic work, and basically here we will say only like a 2 part of it, which is path-oriented based bounded model checking and set plus LP plus RTSS BMC. Okay, first, path-oriented based bounded model checking. Our method is like that. Like as we say, like the red circle is the complete set space, and the current SM solver. Like if you consider all the possible directions, it may solve only state space like in the blue range, which is too shallow to touch any deep behavior. But now what we do, we say instead of checking all the directions, you may just go one path. You forget about all the direction, just follow one direction, make a pass, and just move on. And in this case, we can check this pass and make this the pass long enough to try to touch some deep behavioral systems. And once we can solve one pass, what we can do? You want to do BMC, right? When you give a fixed number, a fixed value of the bound, the potential the number of the potential passes in this bound is finite. And the most simple way and stupid way, the most straightforward way is just to enumerate all the candidate passes in the bound by DFS, depth first search, right? It's a very simple idea, and it's a trade-off between space and time, right? I just don't want to check everything like together, like in one time, but I just check one pass, then next pass, next pass. Then as it's finite, so give me enough time, I can finish. Okay, that's the first idea. So here, what's a pass? In Hybrid Automata, we say a pass here is a sequence of locations and the transitions. Say we stay in location V0 and we jump to V1 and keeps going on, and we end up in Vn. And when we have a pass, we need to check like whether we have a behavior satisfy everything there. So what's behavior? We add time into it. Says we stay in location V0 by time T0, and we jump to V1 and stay there by T1 and keeps going on, and then we go to Vn and stay there by time Tn. Okay, so we now want to find a set of valuations of t and all the variables to make this behavior feasible. So what we do here is we make an abstract of the continuous space. Like for V1, we don't check on like all the time spots. We just build two sets of variables, which is data and which is data x and gamma x. We say like whether we can find a set of valuations, data 1x, gamma 1x, data 2x, gamma 2x, data 3x, gamma 3x, and so on. Which means when we enter location V1, the valuation of everything is data 1. And when we leave it, the valuation is gamma 1. And then we jump to location V2 with data 2. And we leave it with gamma 2, and so on. And for each location, like for V1, say we have some differential equations like dxdt in the range from 1 to 2, and dy dt is equal to 1, and the invariant is y smaller than 5. We can build inside constraints to make all the invariants and the transition guards be satisfied. Say gamma 1y equals to data 1y plus t1, because dy dt equal to 1, right? As we stated by t1. And we have data 1x plus t1 smaller than or equal to gamma 1x and smaller than or equal to delta 1x plus 2t1, because we have such flow condition dxdt in the range from 1 to 2. And we have t1 is non-negative because it's time. You spend in this location by time t1. The time cannot be a negative one. You cannot say I stay there by like -3 seconds. That doesn't make sense, right? So we also have invariance, say y smaller than 5. So we have like both data 1y and the gamma 1y should smaller than 5. And that's it. And everything you can encode in such a way very easily to stand the state space of the system. And here's a simple illustration. For example, here's a model of a water level monitor, and it has like 5 locations. We have a variable y here, which stands about the water level of the water in the tank, and x is a timer to see how long it happened, like since the last signal or something like that. So we have say like first the the word label is 1, then in location v1 we stay there by some time, and you should keep y smaller than or equal to 10. And once y, the word label, touch the level of 10, then x is resetted. And in this case, y x is the water level in v2 is still going up by dy dt equal to 1. But then the time should keep in like 2 time units. And then when x reaches 2, then y starts to going down. The water level starts to going down. And when the water level reaches 5, then the timer is reset. And after 2 time units, it will go up again. And the question here is whether it is possible for y to reach 0, which means the tank is sink. Okay, so the target here is V5. We want to check whether V5 is reachable or not. So we have one pass, V1, 2, 3, 4, 1, 5, which means we go through this loop and go to V5 finally. Then we build the behavior. We introduce a set of variables Ti, T1 to T6, and we also have the constraints. Ti should be non-negative. Then we have some variables like the gamma and the delta, and we have flow conditions. For example, for V1, we have dy dt equal to 1. So we have gamma V1 y plus T1 equals to gamma delta V1 y plus T1 equals to gamma V1. And we also have invariance, which is here. For example, we have y smaller than or equal to 10. We have both delta and gamma should satisfy that. And we have transition guards. Like for E1, we have y equals to 10. It means like only when y equals to 10, this transition is enabled. So gamma V1y should equals to 10. And we also have reset. For example, here E0, we have y reset to 1. It means delta V1y equals to 1. Things like that. You can generate all the constraints of that straightforwardly. Okay, you may ask, like when we talking about hyperautomata, we say the most difficult part is the continuous part, right? We have the delta, which means the value in, and we have the gamma, which means the value out. How can you make sure that the continuous state space between delta and gamma makes a feasible behavior? The thing here is we are talking about linear hyperautomata. So what is linear hyperautomata? Every constraint is linear, and even the flow condition is dxct in a range of real numbers. In this case, all the state space, all the constraints, space are convex. Then what we have? We give like several convex set, and we put them together. The conjunction should still be convex. And given 2 points in the convex set, you can just simply get a straight line which collects these 2 points, and all the points on the straight line stays in the convex set. Okay, that's the reason we can simplify the state space of the continuous part to 2 states. Once we find these 2 states, we can make sure there will be some feasible behavior to collect them. Okay, so here we transform the path-oriented reachability into the feasibility of a set of linear constraints. And as everything here is linear, we can check them by linear programming efficiently. And in this case, we can touch the deep behavior of the system, like by one pass. Then we can just enumerate the pass, right, to do everything else. Okay, so here comes our second part, which is DFS-based bounding model checking. And the first stop we have is eager DFS BMC. Why we call it eager? Because we check for DFS, we check each pass row in the given bound. If row is infeasible, then we backtrack to the last location, which is a very typical depth first search. Right? For example, here we're starting from location 1, and we check whether 1 is good or not. If it stays good, then we keep moving on to 2. And we check 1, 2, whether it's good or not. If it's still good, we go to 3. If it's not, we backtrack, something like that, right? It's a very classical DFS. And here's an illustration. For example, we check V5 in bound 6. We just go into from V1, yes, 1, 2, yes, 1, 2, 3, 4, 1 again, and 2. And here it touches the bound 6, right? So we backtrack. We find another one, which is 1, 2, 3, 4, 1, and then 5. We find no, then we backtrack again. Then we have only 1 pass left, 1, 5, and the result is no. So it means the target V5 is not reachable in the given bound. Okay, in this way, the memory usage is well controlled, and the reason is we only keep the ongoing pass in the memory because we are doing DFS. So we don't need to remember everything, all the other branches. We just go follow the direction, follow the ongoing direction, right? So we will not use lots of the memory space, and this method is guaranteed to terminate because you are doing BMC. It means the number of potential passes is finite, so you can enumerate them one by one, then you can finish the checking. Okay, so basically, as I said, it's a trade-off between space and time. And by this very simple idea, we build the first version of our toolbar, which means like a boundary reachability checker of linear hybrid automata. It has a GUI to draw the automata to write everything, including variance and the flow condition and so on. And the tool is also public available on the website. And okay, here's a graph structure of our tool. It's a Java-based tool. The first version is a Java-based tool, and it's using our 124 LP solver, and it has graphical LH editor and the reachability checker. Basically, it do the syntax check, then it generates the LH model, then it goes to a parser, and the user can do pass-oriented or functional check. That's it. And we will skip the part. Okay, how does that work? That's a question. For the eager DFS plus LP, we check each pass row in the given bound. Actually, we found it has lots of redundant work. Why? Let's see this example. We want to check whether V5 is reachable or not, right? When we do the V5, if you remember the illustration I just gave, we check pass 0 to 1, then 2, 1, 2, 3, and so on. Actually, before we check the pass reaches 5, we do a lot of LP solving for different pass segments to see whether the prefix of the pass fitable or not. Compared with DFS of the graph structure, LP solving is very time consuming. DFS is quick, right? But once you find a new pass segment, you do the checking, you will call the LP solver, you will wait for the result, right? It takes a lot of time. You still remember this picture, right? When we check V1, 2, 3, 4, 1, 5, how many LP solving we do? 1, 2, 3, 4, 5, 6. We do 6 times of calling over LP solver to see whether prefix is fitable or not. Okay. So here comes the question. For these 6 computation of the LP problem, can we save it? And then we come to our second solve, lazy, DFS plus LP plus RS. What's that? So our first thought is like, can we only check the pass row when it reaches the target? That thing is like, if you want to check like for one point, you don't do like all the checking all the way. Like for example, we want to check like whether 1 is reachable or not. We just keeps going on, and when it reaches 1, we could do the computation to see whether it's reachable or not. That's our idea. In this case, we will not to check this part, and so on. We are wondering whether in this case we can save the time, and not always the case. Why? For example, let's see this picture. We have 1, 2, 3, 4, and for 1 and 2, we found it's infeasible. What we'll do? What we do is we find it's infeasible, then we jump to this point because we know it's infeasible. It doesn't make any sense to keep moving on, right? So we will backtrack to this point and keeps going from the blue parts. But if we don't do that, what will you do? You check this, you find, okay, the complete path is not feasible. So we will backtracking. The place you backtrack can only be here. That's the problem. Because you may travels the deeper subtree and you may end up there because it could be huge. You could spend a lot of time, but that's meaningless because the first part, the prefix of the path is infeasible, right? So the question is, how can we backtrack to the right place if we don't do all the LP solving step by step? Okay, here comes our method, IRS. We're using IRS to locate infeasible path segment call to accelerate the backtracking. What's IRS? IRS is an irreducible infeasible set. An irreducible infeasible set of an infeasible linear constraint set is an unsatisfiable set of constraints that will become satisfiable if any constraint is removed. For example, here, we can see constraints like A, B, C, and D here, right? If we put A, B, C, and D together, then the complete set is infeasible. But actually, the constraint D here is really innocent. It has nothing to do with to conflict with any other constraints. The reason here is A, B, and 3. They are conflict with each other. So here, A, B, C is an RS. First, A, B, C, put them together. It's infeasible. And then you remove anyone from A, B, C. This left part are feasible. Okay. So what we do now, we want to use this method to extract the infeasible path segment. You may recall we used a linear programming-based approach to check the feasibility of a path throw. The ICE technique can be used where? Can be used to locate the minimal inconsistent set. Such inconsistent or infeasible set can be mapped back to a path segment. As we can see, like all these linear constraints are coming from one of the syntax elements in the model directly, right? So once you say, oh, this one and this one are conflict, then we can say, okay, constraints in this location makes trouble. Okay, here, for example, we have V0, 1, 2, 3, 4, 1, 5, right? Here, it's a pass, and that's one from going to this loop and go to 5. And when we're using our method, we can tell 3, 4, 1, 5 is IIS because these path segments can generate some constraint that makes the whole constraint infeasible. So what can we do now? Because for an IIS, you remove any one of that will make the left part feasible. So what we can do is we just remove the last node, which is V5, and we backtrack to V1. Okay, and also we can do bad example guided backtracking. What do we mean? Once DFS found a new path containing this IS path, it will backtrack to the location directly with call LP solver later. Then, is this method the best solution? Still, not really. Why? For example, in this graph structure, we say 2 and 3 are conflict with each other. So you may do what? You may just backtrack here and then backtrack there. In the future, you may travel 2, 3 these path segments again and again and again. Right? For example, for this simple model, when we do lazy DFS plus LP plus RS, the path enumeration part gives us 24 passes to check. And how many times we call it LP solver? Only 2 times. What does that mean? That means first, the bad example guided travels works because we have 23 passes are refused, not by LP solving, but by the bad examples. For example, here, 2, 3, 2, 3, 2, 3, and so on. But the question is, are there any method that we don't need to traverse these bad examples? Because we already know if we found that path segments, it will be conflict. Are there any way that we can refuse them in advance? That's our question. Is these passes containing the ions are not feasible for sure? Can we don't waste time in enumerate such passes? Okay, then it comes our another main method, which is step plus LP plus IS plus BMC. Here we use SAT instead of DFS to enumerate the graph structure. How do we do it? Actually, the transition relation graph of the linear hyperparameter can be encoded as propositional formulas. What we do, we encode the boundary graph structure of LHA into a propositional formula set. Then we find the truth assignment using a set solver. Then we decode the truth assignment to get a path in the graph. For example, the clauses we have. First, we have next. It says for all the locations, location now equals to Q. Then it will implies for the next step, the location prime will equal to Q prime. What kind of Q prime? We have Q and Q prime in the transition, in the jump. And we also have exclude, like location equals to Q now, it implies location cannot be any other locations. You can only stay in one location at a time. And we have initial, says, okay, the first step location should equals to the initial location. And also we have the exclude because the first step, it cannot be assigned to other locations. And we also have the target. So the bounded graph formula set which bound K can be right like BG K equals to like the first step in late clause is true. Then the next clause should be true for the next moves, and also the exclude, and then during the time that the target may be true in some time, something like that. So still this example, the water level monitoring system, we have like for the first step, like V0 should be true. And the other location should be false. They cannot be true in the first step. And for the next, we have like the first step, you are in V0 means the next step you could be in V1, right? And we also have things like the first step, if you are in V1, it means the next step you could be in V2 or V5 because it has two successors, V2 and V5, something like that. And our target is like you either in V5 in the first step or in the next step. That's the set encoding of the boundary graph structure of the system with bound 1. And then we can decode for the truth assignment. The superscript of the name of variables represents the order of the nodes in the past. Suppose we get truth variation, we say like if satisfy V0, the first step, then V1, then V5, then we can have a pass, V0, 1, 5, and so on. As we have exclude, so it can never happen like two nodes are the same for the same superscript, right? Because we have the exclude clause. Okay, so we can enumerate potential passes using set-based approach, and then we can check the feasibility of an abstract pass using the LP-based pass-oriented analysis technique. Then what we do, first, feasible, it means reachable. How about not feasible? If it's infeasible, then it means the target is not reachable, right? And in DFS, we will do backtracking. And now we are using set. How do we do the backtracking? Here, we exclude the confirmed infeasible passes. We exclude a new clause, include a new clause to prevent set from enumerating passes which have been proven to be infeasible. The infeasible clause and the updated boundary graph formula like this. For each infeasible pass row, we have like infeasible row should be true for the case steps, and then we just put it back to the bounded graph structure. You just put it back. Then the set solver will, because it already says it's null, right? So it will not to generate the path which contains it. For example, here we have an infeasible path from V0 to V1 and then V5, the one we have talked numerous times. Then the encoding like this. We say for this path, we have like a V0, if you are true for V0 in the step I, and V1 in I+1, V2 in I+2, and so on, then V1 on I+5, then you cannot be true on V5 on step I+6, right? I just put this constraint back to the set encoding. Then in this case, it will never give us a path which contains such segment. Okay, here, infeasible paths, which will generate infeasible linear constraints, right? So when we have infeasible linear constraints, we can have IS constraints. And when we have IS constraint, we can have IS paths. And as we say, any path which contains an infeasible path segment is infeasible. So we can add IS paths back into the graph structure to dismiss all the passes which may have such path segments. So we introduce a new IS clause to prevent the set from enumerating passes which contain an infeasible path segment. And what we do is like this. We have a IS clause, and for all the IS paths, we have a big conjunction of them, and we put it back to the bounded graph. And the previous check path is this row, right? And as you may remember, the infeasible path segment is from 3, 4, 1, and 5. And then the IS clause is if you are true in step V3, in step I on location V3, and you select to go to V4 in the next step, and then V1 in the steps of that, then you cannot go to location V5 in step I+3. Right? In this case, all the passes which may contain such path segments can be refused by the set solver. Okay, for example, still this example. We check V5 and the bound is 100. And when we do DFS plus IS, we check 25 passes. We call LP 2 times, right? If you remember, we say 23 passes are rejected by the bad example. But now here, the set plus IS only generates 2 passes. And we just check these 2 passes and say no more passes anymore. It's done. Okay, now we give some case studies. First, based on this idea, we build a new tool which we call BarSat. It's we use IBM Cplex Optimization Studio as the underlying LP solver and IS solver. Actually, IS is very mature technique. We can find many methods with polynomial complexity, and we're using miniset to do the set solving. And here we have cases like train control systems and the simple automata and the highway systems. And for the train control systems, in like this way, it's not very complex. But of course, we have loops inside. Otherwise, it will be too simple. And you can see for this system, it has like 8 locations and 2 variables. And if you compare with Spark and the integral solving by using SMT, like we generate a huge SMT methods. We also use MathSet and these 3 to solve such problems. And if you do that way, for a system with bound like 500, we can see both BarSat, MathSet, and these 3, they can solve it quickly. But for back DFS, it's out of time because there will be too many passes to enumerate, right? One by one. But if you're using our method, the BarSat, if we just enlarge the bound from 500 to 4,000. The time process used is 392 seconds. And for MATSAT, it used like more than 1,000 seconds. For Z3, it's out of memory. We may know that here for bar, it's out of time. And the memory here is only 200 M. But for Z3, it's out of memory because the problem is too large to handle for Z3. But however, if we continue enlarging the bound to 8,000 steps, and Bob still can solve it in like 2,000 seconds, while MATSAT also out of memory. Okay, that confirms our idea that Bark can always control the memory very well because it can only need to keep only like the ongoing path in the memory. So the memory usage is not that large. But if we do DFS, it will be very time consuming because there will be too many passes to enumerate. But with our help, BoxSat can do it quickly. But compared with using like a SMT solver to solve such problems by one time, then they will face the problem of out of memory because the problem will be too huge. And the same story happened with the sample method. We will skip it. Basically, very similar thing. And the thing we really want to talk about is the highway system. This system is a very interesting one. Why? Because it's a scalable system. It has a location here says V1. It just models like a sequence of cars on a highway. Like each car should keep the distance between the previous one and the following one. And if they find that two adjacent cars are too close, then it will ask the car ahead to accelerate and the car behind to decelerate, something like that. So you can arbitrarily enlarge the system to introducing more cars into it. It will make the system very large and difficult. And so we consider it as a wonderful case study to see whether our method is scalable or not. So first we check the system on a system with like 100 vehicles. By 100 vehicle, we mean the system has like 102 locations and 100 variables. So you can see it's very interesting. Like for such systems, even with bound 30, with bound 30, but DFS out of time because the system is too large, right? 100 locations, 100 variables, then there will be too many passes to enumerate. That's a problem. And if you with 30, then MATSAT and this we can still solve it, but the time is already large. But once we enlarge the bound from 30 to 100, but DFS out of time. No. But MATSAT and Z3 out of memory because too many passes. The too large, the problem is too large. But for BoxSat, we can still solve it in 1 second, not 2 seconds. And then we continue this inquiry enlarge it to 3,000. We can still solve it in 1 minute. And we keep enlarge the system by introducing more cars into it. It makes 500 locations and variables. And BoxSat, even for system with 500 locations, we in the step like 200, we can solve it in like 74 seconds. And but DFS out of time with bound 100 and MATSAT out of memory with step 3, and Z3 also out of memory by step 100, which also confirmed our idea that if we do the integral solving by put them to one problem, that will be too difficult for the existing SMT problems. And our way of path-oriented checking is feasible in lots of cases. Okay, this we will use as underlying checking methods to solving real case CPS systems. Actually, for CPS systems, we we use these pass-oriented methods. We use these set LPIs methods. We also use many other methods, including like we introducing a shareable guided synchronization semantics for solving like a network of hypermethods. We also introduced like checking of nonlinear systems of like convex systems, and we can not use linear programming but convex programming. We also introduce more methods to solve hybrid automatas in under different restrictions, and then now we use them to solve CPS. Okay, so now we finally go to the second part of my tutorial, which is online model checking of subcritical systems. And the outline of my talk for this part is about, first, I will show motivating examples, two motivating examples, and we will show our online modeling and verification of such systems. And we will solve this method by optimized by two aspects. One is performance issue, one is how to solve the state coverage issue. Okay, CPS. What is CPS? CPS, I assume like most of the attendees in RTSS knows about CPS. CPS is a combination of computation, communication, and control. It's like basically model system working in an open environmental open environment. It's complex systems, and it has also been widely used in safety critical areas. For example, train control, medical systems, and also lunar rover, something like that. It works in very complex environments that will like to receive signals from the context very frequently, and then will compute, do the runtime computation, and to do the control. And for things like that, we really need verification to make sure they work correctly. Okay, here first, motivating example one. It's communication-based control systems, which is using in train control systems. The picture is I borrowed from some of the engineers in the train control systems in that industry. Okay, here we have many trains running on the single track, and we can see the red bar here, green bar here. The green bar means the movement authority. What's the movement authority? It's term used in train control. It says like before next communication with central control center, this train can only reach this point. This is authority to your movement. You cannot move beyond. You cannot move beyond these green parts. And we also have some safe braking distance. It says like what's used for? It's used for like to say if you start to do the braking now, you considering your current velocity and something, you may stop by the end of this SPD points. And we also have rear safety distance. I mean, you can see the movement authority of each train, and it doesn't just touch the train ahead directly. It still have some distance in case you will move beyond the MA, something like that. And the thing interesting here is everything here, the movement authority, the rear safety distance, and the safe braking distance, they're changing continuously. What do we mean? Because the communication is continuous communication. You will communicate with the train control system very frequently. And once you've done the communication, you will get new movement authority. You will do all the computation very frequently. And here is a specification we get from our friends our colleagues in the train control industry. It says in such systems, the RBC, ZC, zone controller, it means the control center. You can just think about it as control center. The RBC and ZC will try to update their respective trains movement authorities and end movement authorities in every 500 milliseconds. It's very fast. And on receiving an update, a train's onboard system derives a legal operation speed range. Then we have two safety rules. Safety rule number one, once the SPD point is reached, the train must brake in standard procedure to attempt to stop before EOA, end of movement authority. And safety rule number two, if the train has not received movement authority update from the controller for 5 seconds, the train will assume the connection channel is broken because it really depends on the communication. Like it gets signals every 500 milliseconds, so the train will brake emergently. So we have two questions. The engineering are asking questions about question one. When a train enters the safe braking mode, whether it will stop completely without move beyond the EOA point. So the question is talking about like whether the train control function they design is correct or not. Like given different inputs, whether they can make sure that the train can stop before move beyond the move MA point. And question two is, when a train does not receive any signal for 5 seconds, it will brake, right? But whether it may still pass EOA point or even collide into the train ahead, like this. Like the communication is done, then the train after 5 seconds, it notice that maybe it is done because it has not spoken with the train control center for 5 seconds. Then we will do the emergent braking, but will it be too late? Can it even collide with the train ahead? Okay, that's the first motivating done. And here we go to the second one, MDPMP, medical device plug and play. Actually, thanks to the advancing of the sensors and the real stuffs, you can see now if you go to the hospital, there is lots of numerous isolated advanced systems items like PDA, tablet PC, workstation, medical station, BP, barcode scanner, infusion pumps, oximeter, monitors, and so on and so on. Lots of numerous different devices. Like every time I go to a hospital, I can see something I haven't never seen before. Okay, and for CPS here is we aim to combine them together to build a CPS systems. We take a very simple surgery operation, for example. It's we have a surgeon. It's a person, right? He has a laser scalpel. He or she has a laser scalpel, and he will use this laser scalpel to do operations in the patient. And during that time, we will have a SpO2 sensor and the O2 sensor to check the blood level of the patient, right? To keep him or her alive. And when we find the reading is too low, the ventilator will pump in the oxygen into the patient, and everything is controlled by the supervisor, computer. Okay, it's not person, it's a computer. Okay, so benefit is it can increase safety and efficiency and ADC, right? Definitely, we have lots of devices to do the monitoring, to do the communication, and so on. But here we also met two safety rules. Safety rule one: when a laser scalpel emits laser, the patient's trachea oxygen level must not exceed a threshold. Otherwise, what would be? It will be a fire, right? If the oxygen level in a patient's trachea exceeds a threshold and you emit a laser, it will be a fire. That would be very. That's the last thing that we want to map, right? And safety rule two: the patient's blood oxygen level shall never reaches below a threshold. You cannot say, okay, I just want to to make sure that the oxygen level in this trachea area not that high so that I may cause any fire. So I will just wait some time. No. If we wait too long, the oxygen level in the blood will drop down quickly. Then that will be a suffocation. The patient will also die. That's very dangerous. Okay, we have two systems now. So let's think about what's the behavioral system. First, about the train. Actually, the train, if you goes to the driving cabin of the train, you can see it has lots of discrete logic control. It also have continuous real-time behavior, right? Put them together, hardware systems. As we say, hardware automata. We can use that to model such systems. So our idea is like hybrid automata is combined of discrete logic transition and it has continuous real-time behaviors. It's the most natural model for modeling language for CPS systems. So our first stop of the target is to model the target CPS by hybrid automata. And we verify it by model checking, because in the beginning, what we do is we do model checking of hardware systems. So for such systems, for model checking, what we do, we have a system like train control systems. We have a specification like no collision. Then we build the model into hybrid automata, and we express the specification as a state, whether the state is reachable or not. The best state, collision, whether it's reachable or not. Then we put into our tool like bar, we input passes, we check. If not reachable, then good. Reachable, we give the pass. That's the way we are thinking about that. Yeah, that's a story we're thinking about. Then, is that true? Not really. Okay, here is a model we build for the systems. The A part is about the train control systems. The B part is about the ZC, right? We have we have the first trains waiting for the movement authority, then do the computation after it syncs with ZC by update MA. It reads MA. Then do the computation. You see, okay, the operation range for me for the next cycle should be like N to N prime, something like that. Then we'll add adjustment, and then we'll do the cruise, and then we'll see, okay, if I already reached the SPG point, standard braking. If the time I communicate with this is 5 seconds, then we do the e-braking, and so on. Right? This looks like a hybrid automata. And we have two specifications. First, we want to check whether the location is braking constraint the train I place position larger than MA for the safety rule 1. And this is for the question 1. And the location E braking and the train I, the position of the train I is smaller than the position of train I+1, which is collision, right? For the specification 2. We do the verification. First, we make the computational state space explosion because we have dozens of trains on a single track. And we also made nonlinear functions because all the train control functions are nonlinear. You cannot see anything like a dxct equals to 1 in train control systems. It's difficult to verify. And that's not the difficult part. If that really only computational and nonlinear, we can do nonlinear hybrid automata check. We do have checkers there, right? I don't have, but we do have that on the shelf. The most difficult part is non-deterministic behavior. When they do the train control system, so they do the computation, they will consider like the values of like wind speed, mass of the train, whether it's running or not on the track, something like that, into the train control system, into the train control function. They will use these values to do the computation. And that makes it difficult to model. Why? Because it means the system is not a concrete model. It's a system, it's a model of a system with 3 variables. Okay. How about the surgery systems? Okay, we build a model for the ventilator. It can pump out and pump in, and and when pump out or pumping, the height of the ventilator is moving according to some differential equation, everything goes fine. Then we build the patient. We met problems. The patient, according to the pump in, pump out, and hold, the patient also has like inhale, exhale, and hold, right? So now we build the oxygen level of the patient in the trachea. Luckily, we found some medical books and medical papers. Actually, they do have a differential equation for that, about the differential equation about the values of the oxygen levels in the trachea. But when we want to do the modeling of the SpO2, which means the blood level in the oxygen level in the blood, we found a problem. We do find statements say blood oxygen level is strongly affected by complex human body biochemical reactions, even emotions. They say low way to model SpO2 in a low room. Basically, that's the same thing. It's a model. We do have a hybrid model, but it's not a concrete one. It's a model with 3 variables. Okay, what we do? With this model with 3 parameters, it means we cannot do the traditional offline model checking to do the traditional computation of the complete state space offline, right? Because you don't know the values of these variables. So here comes our story, online modeling and the verification. So our story is we do not do the traditional offline modeling and checking. We do online periodical real-time hybrid system model checking of time-bounded short-run feature. The traditional model checking is offline and it consider about the long-run feature, either the state space forever or the state space in non-run case steps, right? But now for us, we only do we do online periodical real-time checking, and we only consider short-run features. So the challenge one, there we say no good offline non-run models for non-deterministic parameters. It's solved. Most vital signs, online short-run behavior is easy to predict. I cannot tell you what it will be like in 5 minutes, but for 5 seconds, it's easy to predict. And challenge 2, verification state space easy to explode, but now we only do online and short run. It fixes many parameters and it shrinks the state space by a lot. Okay, here is the picture. For the classical control loop, we have a running systems and we receive instructions. You either using collect values from sensors and actuators, or you compute by call control functions. Then you get a new value of parameters, then you just deploy, use it. But now what we do, we introduce the right part, the blue part, we call it runtime monitor. When you have a new value of parameter, we will put these parameters into the parametric model of the systems. Then we can have online modeling module to bring it to a concretized model. But the concretized model, it cannot last for that long because the parameter, the values of the parameter may change very quickly. So this concretized model can cover only a short time in the future. So what we do is we do the online verification of the predefined verification task to see whether the concretized model is safe or not. If we find it's not safe, we will reject these parameters and ask the system to call a fallback plan. Like, for example, in the train control systems, we will just stop the train. Just stop the train. And for the surgery systems, we will do is like we stop the surgery and keeps pumping oxygen to keep the patient alive. Okay, that sounds promising, and that we really can solve problems. And we find we face several problems. The first one is performance issue. because you do periodically online verification, so the verification must be fast. The modular updates every 3 time units. It's periodically, like for each train, it's 500 milliseconds communicated with the control center. And for the human, it will change like every few seconds, something like that. And if we cannot finish online model verification in D time unit, the result will be useless. First, D cannot be larger than T, right? If D is larger than T, then when you get the result, it has already used another set of parameters, and D is useless. And the D, okay, it can smaller than T, but it should give you enough space, because if the D's and T are really close, then you just have like 1 milliseconds to do the callback plan. That's not enough. The first way we saw is we solve it by hardware. We do multiple-based assignments, basically for the running systems. For the general behavior module, we put in one call. For the control function computation model, for put in call. And for the online modeling and framework modulars, we put the different problems in different calls. For each call, we just put the online modular just get the values and put in the corresponding scenario, the model, to generate a new model and to the checking and to return the result. That's a very straightforward idea, right? We're using just a multi-code to do it. And here the thing we really want to solve to talk about in software level. In software level, we do two things. The first, we have discussed with many engineers in the industry, and we find that the thing they're really interested is whether the system can sustain many safety critical scenarios. And by scenarios, that's just a computational path for each component. And in this case, all we see is we can do incremental solving. What do we mean? The state space with respect to different cycles are changed slightly. Actually, for system like in cycle 2 and cycle 3, or cycle 1, right, compared with the cycle before and ahead, the main components in the system cannot change that dramatically. The thing that change are just some number of components in the system or the valuations of the variables in the system, and so on. The other parts are the same, right? So suppose for the cycle 1, the model is M1 and state space is S1. You want to verify whether S1 set by row or not. And for cycle 2, M2, the state space is S2. You want to check it again. So now we transform the problem of whether S2 set by row into whether S1 plus delta S set by row or not. And here, delta S is the difference between S2 and S1. You may remember the underlying technique for bar is linear programming, or you can using SMT, and so on. So we can take advantage of incremental linear programming to accelerate the verification of the loop cycle. For example, for a scenario, like for different component like S, T, and K, right? So say S, T, and K is a component in the first level, and in the second level, L comes out. L joins the system, and T quits from the system. That's possible to happen because, for example, for train control systems, S and K are still running on the track, but T goes into the station and L just departs from the station, right? In this way, what you will need to do is you need to recalculate the synchronization between these components and to update the related synchronization constraints accordingly. And for example, for the T, all the constraints about T should be removed from the constraints, and the constraint about L will be added in, and we'll have the synchronization of the event edge and so on. You will update them, you will delete them, and you will add some new. And okay, that's a simple idea. So we implement a new version of the tool we call it Bug Online. We it has a graphical remodeling of the parametric hybrid meta. It has APIs for online verification, and you can see here we have you can write the change rate is in C1 to plus N1, something like that, where C1 and N1 are free parameters. But then if you concretize it, you will see it's 11 to 15, something like that. Okay, and we do the evaluation for the train control system. So our method can solve a system with 10 trains in 100 milliseconds, which is more than the cycle 500 milliseconds. And for the laser scalpel systems, we can handle it in 1 second, which is also smaller than the cycle reported in medical papers say 4 seconds. They say the blood oxygen level in 4 seconds are predictable, but after that it's not. Okay, that's a performance issue. Now we handle the state coverage issue. What does that mean? The state coverage issue here, like you see, we check the behavior of T1 in time D1, and then after that, when the value parameter are changed, then we check T2 in D2 and so on. But in this case, the time you do the checking, D1, D2, D3, the systems are locked under safety cover. It's not checked, right? If anything happen now, it's dangerous. So under this consideration, we do a pipeline design. What we do is we do not start the checking from after the end of the T. We start from half of the T. We do the checking in D1 in this time unit for T1, and in the middle and after D1 is finished, we do another round of checking for this part for T2. And in this way, when we do the checking, the system is safe under the previous checking. Then it will be a pipeline continues to cover all the state space. And on this consideration, we also bring to design. The first one is hard real-time system design. And here is the code of the system. It says, okay, for the main loop, we wait till current time t satisfies t mode, half of the big T equal to 0, which means we wait to the middle of the T. And we read the sensors, we build the model, and we do the checking. If A may reach unsafe states in range T0 to T0 plus T, then we switch the hardware system to fallback plan, which means we have finished the verification and we know it's unsafe. Then you call the fallback plan. Otherwise, we allow the system to run normally. What does the otherwise means here? The otherwise can be we find the system is safe. And you may still remember the verification of a hybrid meta is undecidable. Even for BMC, it's very complex. It's decidable, but it's very complex. It's not guaranteed to get a result in a few in a limited time. So maybe for that system, it can be like it takes too long. It cannot finish in the T time units. In this case, we still allow we allow the hardware system to run normally. This requires the verification must finish in D. Unfortunately, for hybrid automata verification, this hard bound shall not exist, right? So the second one is the soft real-time system design. What we do two ways. One way is conservative way. The other is aggressive way. For the conservative way, what we do is we still read the sensor, we build the model, we do the checking, and if the model is conservative way, then if the A may reach unsafe states in this time unit, or the current time T is larger than T0 plus half of T. That means what? That means we have not get result from the previous checking. It has not finished, so we don't know it's safe or not. So if we do conservative way, you switch the hardware system to fallback plan. you haven't given the get result, it means you may face the risk that the system is unsafe, right? So you call it stop. Else, if you do the aggressive way, that means it may reach unsafe state space in this time unit. Then it may not reach the unsafe state space. That means it's safe. Or the current time t is not there. That means we have not finished the checking, but I choose to face the risk. Then allow the system to run. Else, we switch the system to fallback plan. Okay, so in the conservative methods, it means there will be no accident, but you may face a problem of false alarm. But in aggressive way, missed deadline means the risk of accident, but you will face no false alarm, right? So we do a evaluation on 1,200 second traces from physio-led real-world medical traces. And also we have asked a student from Hong Kong PolyU to do the simulation to Intel, Excel. We connect the data, and the sampling model checking period is 4 seconds. And here's data. And for on the physio-led trace, the number of missed deadline is 2.2%. And for the Hong Kong PolyU is 1.7%. And we also have the execution time of those cut deadline. And we can see like 97.8% of the verification are finished in time. From the conservative way, it means first, no accident, and the false alarm is more than 2.2%. And if you consider aggressive way, it means the probability of reaching unsafe state is reduced by 97.8%. Okay, actually, we also have a real deployment of such method in train control systems. We have a collaboration with National Engineering Center of Train Control Systems in Beijing Jiaotong University in China, and they have a hardware in the loop simulation platform. And that platform is first, it's a simulation platform. It's not real train. Then the second point is simulation platform is the main functionality of that platform is like they will deploy the exactly the same train control systems on the platform with commercial ones. Like when they want to deploy commercial one, they will put it in this simulation platform first to check whether it works or not. And during the experiments, the engineers in that lab, they introduce many bugs into the systems, and our online checking methods can capture this data and report to can predict that the train may collide with the previous one, and then report it to the current train. The train can do braking to keep it safe, and it works really fine. And that makes us very happy to see our method really works on real case CPS systems. Okay, so for this part, what we do is we do like from offline modeling and verification to online modeling and verification, and we change non-deterministic to periodical deterministic, because for the long term it's not deterministic, but for each short term it's deterministic, and we can do the checking. And we have case studies on real case CPS systems, and it's feasible and efficient. Okay, then basically conclude our second part. Okay, here now let's talk about some other ongoing extensions. First, what we do is we do from linear to nonlinear. So you can see like for the previous part, we call what we just discussed about on verification of linear hyperparameter. But many existing systems are nonlinear. So first, I will say we proposed a class of convex hyperparameter. In this class of hyperparameter, we can use the symbolic encoding and take advantage of convex programming, just similar with our linear programming. And for other arbitrary nonlinear systems, which is not convex, what we can do, basically, we are not doing verification of such systems. We know there is many tools which do a very good job, like a Flowstar and so on. What we do here is we do falsification. We use derivative-free optimization techniques to looking for a solution for such paths to make it feasible. But as we using DFO, it's not complete. It's some but not complete. So we will not call the verification code falsification. Okay, that's about nonlinear. And we also, as you may notice, we do bounded verification right here. But we also may face many unbounded problems. But in our method, you can see if we can stop the path enumeration without touching the bound, the stop is not reach. The specification is not reachable in general. It means what? It means like if you go to the go by the DFS and say the bound is 200 and you go like 10 steps, you find nowhere to go. You don't have to keep move on to say like target is not reachable in only like a few steps. You can say it's not reachable in general. Why? Because there is no more paths to go. Based on these ideas, we bring an LTL verification method on the graph structure to block the target node by as passes to prove there will be no other possible passes to go to the target node by considering all these already known infeasible path segments. In that case, the system is not reachable in general. That's what we are doing. Actually, we already have a work on that. It's actually published in RTSS in 2014, I guess. Yeah, and that's about the verification. And for the CPS part, we do like recently we have extended our work not only CPS but to IoT, Internet of Things, like to check whether the Internet of Things, like for example, home automation is correct or not. And we are also doing online control synthesis. Like you may notice here, when we find the parameters are not safe, what we do? We just start a fallback plan. Like for the train control systems, we found you may collide with the previous one, so you do emergent braking. But actually, if you are really riding on the train, if the train do such thing, it will be not a very good feelings for the passengers, right? It will stop, just stop. We in the middle of nowhere. So what we do here is like we do the online control synthesis to generate a set of control parameters to control the system to keep going on, to move on until you pass that unsafe state phase. Then we put the control authority back to the system. And we are also working on that to see whether it works or not. Okay, actually, the work I talk here today, we only give a few points of our whole work. We have a complete systematic work. We have a method from path-oriented to bounded. We have verification from single hybrid automata to composed hybrid automata. We have work from linear to nonlinear. We have also extended work from hybrid system to self-feasible systems. And all these methods are implemented into our toolset BARC, which, as I mentioned, is a boundary richly checker. And BARC, currently we have published a series of papers in like TCAT, TC, TCPS, TPDS, CAB, RTSS, CC, Data VMKI, and so on. And tool itself, it has been like a decade now. It has a graphical editor, model checker, Eclipse plugin, web application, and so on. It has more than 8 components and 30 versions, more than 500 globally download, including researchers from like UC Berkeley, CMU, British Columbia, and also engineers from industry. And yeah, now finally go to our conclusion. So by isolating the discrete paths and related continuous behavior into different layers, the complexity of our approach is well controlled. That's talking about our verification of the hybrid automata. That's our unique way of the path-oriented verification. And by periodically online modeling and verification, we can handle the non-deterministic behavior of CPS systems easily. And as you may see, it's efficient that we can keep the system safe because we can finish the verification like in milliseconds. And all these things are implemented in one tool, and the tool is public available. And it would be a great pleasure if you can try this tool and to tell us like how do you think about it, like any suggestion, and any suggestion will be very welcome to see how we can optimize the tool, and or we can collaborate like in any real CPS systems to solve more problems. And yeah, thanks a lot for your time, and it would be great if you can uh, like send me mails or just try to contact me to let me know if there is any problems or suggestions. Yeah, thank you. Thanks a lot. Bye.